My friends, Alexander Bebaya. Today we are going to solve mathematical equation model 3 on harmonic conjugate. U, function of x and y, is equals to ln x squared plus y squared. Show that U is harmonic. Roman 2, determine the harmonic conjugate of function phi of x such that f of z is equals to UGV is analytic. Now, for us to show that any function is harmonic, that is U. So change in U squared with the change of x squared plus change in U squared over change in y squared should give us 0. Now we have our function U is equals to ln x squared plus y squared. The U dx is equals to first derivative of ln x squared plus y squared with respect to x. First of all, we have to differentiate this using chain rule. Let x squared plus y squared is equals to maybe w. Now U is equals to ln of w. The w will give us 1 over w will give us 1 over w. Then w is equals to x squared plus y squared. The w dx is equals to 2x. Let's combine. First to get the u dx multiply the u dw times the w dx. So that dw is dw and left with du dx. So we have 2x times 1 over w, and our w is x squared plus y squared. So it's x squared plus y squared. Now du dx is equals to 2x over x squared plus y squared. That is first derivative. First, to get the second derivative, we have to differentiate the first derivative. So du squared dx squared is equals to d dx of the first derivative 2x divided by x squared plus y squared. This is how you go about it. Now we have to apply the quotient rule. That a bar b minus b bar a divided by b squared. If I let the numerator to be a and the denominator to be b, so first of all we differentiate our numerator, we multiply by denominator, then we subtract the denominator, the derivative of the numerator times the numerator divided by numerator square. Now we have our a 2x bar times b x squared plus y squared minus b bar x squared plus y squared. If we differentiate x squared with respect to x, we get 2x and y we get 0, then times 2x divided by x squared plus y squared. 2 into x squared plus y squared, then minus 4x squared divided by x squared plus y squared, then square. If you open brackets, you get 2x squared plus 2y squared minus 4x squared divided by x squared plus y squared, then squared. This gives us 2x squared minus 4x squared. We get first of all we get 2y squared, then minus 4x squared plus 2x, we get minus 2x squared divided by x squared plus x squared plus y squared, then squared. That is the second derivative. We find the derivative of u with respect to y. With respect to y, du dy, first derivative of u with respect to y, we get dx dy into ln of x squared plus y squared. Now again, we apply the chain rule. Let x squared plus y squared again is equals to maybe n. Then our u now is equals to ln is equals to ln of n. Du dn is equals to 1 over n, which is equals to x squared plus y squared. Dn dy is equals to 2y. If we combine the two, du dn and dn dy, we get du dy, which is equals to 1 over n. Our n, the value of n is x squared plus y squared, then times 2y is equals to 2y divided by x squared plus y squared. This is the first derivative. This is the first derivative of u with respect to y. Second derivative, we apply the quotient rule. D squared u over d z squared, not dz but dy squared, is equals to 2y bar times x squared plus y squared, then minus x squared plus y squared bar times 2y divided by x squared plus y squared, then squared. When you differentiate 2y with respect to y, we get again 2. So 2 times x squared plus y squared minus, when we differentiate x squared plus y squared, because they are separate variables, we get 2y then times 2y divided by x squared plus y squared, then squared. This gives us 2x squared plus 2y squared minus 4y squared divided by x squared plus y squared squared. Again, this gives us 2x squared minus 2y squared divided by x squared plus y squared, then squared. This is the second derivative. This is the second derivative of respect to y. Now, for us to show that u is harmonic, you have to add the second derivative of u with respect to x and the second derivative of u with respect to y is equals to second derivative minus 2x squared divided by x squared plus y squared, then squared plus. Now the second derivative of u with respect to y, which is 2x squared minus 2y squared divided by x squared plus y squared. This gives us, we have the common denominator, so x squared plus y squared, then squared 2y squared minus 2x squared plus 2x squared minus 2y squared plus y squared minus y squared plus 2y squared minus 2y squared is 0, minus 2y plus 2y is equal to 0. So 0 divided by x squared plus y squared, we get 0, and hence u is harmonic. Determine harmonic conjugate of v is x such that determine the harmonic conjugate of function v such that f of z is equal to jv is analytic. So for us to find the harmonic conjugate, you have to apply the CR equation that the change of u with respect to x is equals to change of v with respect to y, and change of v with respect to x is equals to negative change of u with respect to y. Now du dx is equals to dv dy. Du dx is equals to dx divided by x squared plus y squared. Now our dv dy is equals to 2x over x squared plus y squared. If we multiply this part with dy such that our dv is equals to 2x over x squared plus y squared, then dy, then find the integral of both sides. Now our v is equals to the integral of 2x divided by x squared plus y squared. So 2x integrate 1 over x squared plus y squared dy. If we integrate v is equals to 2x, then the integral, after integrating this part to get 1 over x tan inverse of y over x, then plus a constant, call it a bar. That is the our du dy, call this equation 1. Then our du dy is equals to dv negative dv dx is equals to our du dy was 2y divided by x squared plus y squared. So therefore our dv dx is equals to negative 2y divided by x squared plus y squared. Now we have to differentiate. We have to differentiate equation. We have to differentiate equation 1. Compare the two, but for us to get the constant is equals to 2x into 1 over x tan inverse y over x plus a constant, that function. Now we have x and x, so this x will cancel with this, so we have b is equals to 2 tan inverse of y x plus a constant a function. That is our equation. 2 into 1 divided by 1 plus over x squared, get 1 over 1 plus y squared into minus y over x squared. Then plus our that is a constant. So our dv dx is equals to, if we put this in the same denominator, we get 2 into 1 over 1 divided by, this is y squared now. After squaring, we get y squared over x squared. Y squared over x squared. So after putting the denominator in the same base, we get 1 over x squared plus y squared over x squared. Then y squared then minus y over x squared plus that constant into x squared divided by x squared plus y squared. Then we have minus y over x squared plus that constant of ours. The square x squared cancels with x squared. Now we'll be left with 2 times minus y over x squared plus y squared plus, which gives us minus 2y divided by x squared plus y squared plus that constant. Now that is our dv dx from our equation 1 here, which is minus 2y divided by x squared plus y squared plus that constant. Now we have to keep the two equations. We have to put the two equations, because when our equation of dv dx, we have the equation of dv dx, equation of dv dx, which is negative 2y divided by x squared plus y squared. So because they are dv, they are derivative of v with respect to x, they must be equal. So is equals to minus 2y over x squared plus y squared plus that constant. So, and remember, in our first dv dx we don't have the constant. That means our constant is 0. So now that a is equals to 0. Integrate. So if we integrate, we get that our a is equals to 0. Therefore our v is equals to 2 tan inverse of y over x plus 0, which gives us 2 tan inverse of y over x, and this is our harmonic conjugate. So for us to prove the x, so we have dv dx, which is negative 2y divided by 2 divided by x squared plus y squared divided by x squared plus y squared is equals to the derivative of is equals to minus derivative of u with respect to y, derivative of u with respect to y, which is 2y over x squared plus y squared. So, since our equation satisfies the RC equation, now the function f of z is equals to u plus jv is analytic.